Now here's an interesting situation. If you're calculating the pH of a very dilute solution of either a strong acid or a strong base, you're going to have to take into account the auto-ionization of water, because if you don't, you will come up with bad numbers. For example, if you had a very, very weak concentration of a strong acid, let's say that it's nanomolar, okay? Nano means 10 to the minus ninth. If we just said that it completely dissociated, we would sit there and say, oh, well, 10 to the minus ninth dissociated, and we'd end up getting 9 for our pH, which would be basic, even though we had added a small amount of acid. So it would make no sense. So if we have a very dilute solution of a strong acid, the only way that we're going to get accurate answers is to put in the auto-ionization of water. Okay, what did I just say here? Hydronium ion concentration from the auto-ionization of water is actually more than the hydronium ion that was produced by the acid alone. Because the auto-ionization of water said it should be 10 to the minus 7th. If I had a nanomolar solution, that would only be 10 to the minus 9th. So I have to make sure that I put both of those in together in order to get an accurate number. And the same idea if you're doing the base. The hydroxide ion concentration from the water itself ends up being more than from the very dilute solution of the base. There is a sample exercise which you should go look at that is doing the case for an acid. Okay? I will go ahead and do the one that is a base, because I'm just a glutton for punishment. So what are we doing in number 17? Well, it says it's calcium hydroxide. It's going to completely dissociate, right? They said it was 1.5 times 10 to the minus 7 molar calcium hydroxide. But I have to remember that it is going to fall apart and form 2 hydroxides. So from the acid, from the base, we expect a contribution. It's going to contribute 3.0 times 10 to the negative 7th molar OH minus. Okay, that's what we are going to have to remember. It has contributed this. How is that going to change our rice table? Well, the reaction was that we had water reacting with water. This is the auto-ionization thing. And it should just form hydronium ions and hydroxide ions. So you see, I'm not worried about this in the equation at all. I'm taking the auto-ionization of water and I am going to force this into it. So initially then, I'm going to put in, there's none of this, and this contribution from the strong base is the initial condition. These, their water is a liquid. They don't show up at all. Oh, this is getting weird. Okay, so what's the change going to be? Well, it can't stay a 0, and it can't go negative. So it must go up. And if that's going up, well, I'm afraid this also has to go up. Because if these are reacting to do this, they're going to be creating some of each of these and equal numbers. So this change comes from this auto-ionization. All right, well then what's equilibrium? Well, I just add these up. So this one's X, And this one is going to be x plus 3.0 times 10 to the negative 7. Okay, that brings back Kw, which should be these concentrations of hydronium ion and hydroxide ion, and they should end up being equal to 1.0 times 10 to the negative 14. What we have from this is it's going to be x times x plus 3.0 times 10 to the negative 7. We can turn this into a quadratic equation. It will be x squared plus 3.0 times 10 to the negative 7x minus 1.0 times 10 to the negative 14 equals 0. From this, oh look, x is going to represent the amount of hydronium ion. So H3O plus concentration is x, and I'll use the quadratic formula to find it. So here's negative 3.0 times 10 to the negative 7, which means I only have to worry about the positive square root. And there's that 3.0 times 10 to the negative 7 again, but it's going to get squared, and then it's going to be minus 4ac. Oh, minus the plus, and 4 times this. I think I can actually handle writing that down right now. All under the square root sign, and then 2a. If I put that into my calculator, I'm going to end up with 3.03 times 10 to the negative 8. pH, then is minus the log of the hydronium ion, which is this. So minus the log of 3.03 times 10 to the negative 8. And it's going to give me 7.52. Good. It's not very basic, but it gave me a number that is basic.